A silo, base not included, is to be constructed in the form of a cylinder surmounted by a hemisphere. The cost of construction per square unit of surface area is 4 times as great for the hemisphere as it is for the cylindrical sidewall. Determine the dimensions to be used if the volume is fixed and the cost of construction is to be kept to a minimum. Neglect the thickness of the silo and waste in construction. We're told that the volume is fixed, so we can consider that to be a constant in the context of this problem. Also, we are told that the cost of construction per square unit of surface area is 4 times as great for the hemisphere as it is for the cylindrical sidewall. We can find two formulas, one for the surface area, 2 pi RH plus 2 pi r squared, which would be the surface area of the cylinder plus the surface area of the hemisphere, and the volume, pi r square h plus 2/3 pi r cubed, which would be the volume of the cylinder plus the volume of the hemisphere. The cost would be the cost per square unit times the number of square units for the cylinder plus 4 times the cost per square unit for the cylinder times the number of square units for the hemisphere. So an expression for this cost then would be 2 pi RH plus 8 pi r squared. So our cost is expressed in terms of two variables, the radius and the height. We need to express this in one variable. We could begin by solving for h in the volume formula. So we have V equals pi r square h plus 2/3 pi r cubed. If we subtract 2/3 pi r cubed from both sides, we'll wind up with V minus 2/3 pi r cubed equal to pi r squared h. Now we can divide both sides by pi r squared, and we will wind up with a formula for the height that is V over pi r squared minus 2/3 r. We can now take that formula that we have for the height and substitute it into our cost formula. So we'll have cost equal to 2 pi r times V over pi r squared minus 2/3 r plus 8 pi r squared. Now we can distribute 2 pi r over the parentheses, and we'll have cost equal to 2v over r minus 4/3 pi r squared plus 8 pi r squared. Now, combining like terms, we have an expression for the cost, 2v over r plus 20/3 pi r squared. Now we can find the derivative of the cost function. Finding the derivative of the cost function with respect to the radius will give us the slope of the cost curve. And where that has a horizontal tangent, we can find the extreme values for that function. The extreme value that we are looking for is the minimum cost. So we'll find this derivative and then set it equal to 0. We should probably express the cost as 2vr to the negative 1 plus 20/3 pi r squared in order to make it a little easier to find our derivative. So the derivative will be negative 1 times 2 times v times r raised to the negative 2 plus 2 times 20/3 times pi times r. Or in other words, dc dr will be equal to negative 2v over r squared plus 40/3 pi r. Now we should set this equal to 0 and solve for r. So we have minus 2v over r squared plus 40 thirds pi r equal to 0. We could multiply both sides by r squared in order to remove r squared from the denominator, and we will have minus 2v plus 40 thirds pi r cubed equal to 0. Now we can add 2v to both sides, and we will have 40 thirds pi r cubed equal to 2v. Now multiply both sides by 3 over 40 pi. And we will wind up with r cubed equal to 3v over 20 pi. And if we find the cubed root of both sides, we wind up with r equal to cubed root of 3v over 20 pi. We're supposed to find the dimensions, so we've got a good start on that by finding the radius, but now we need to find the height. Now that we have an expression for the radius, we can substitute that back into the expression for the height. So we have h equal to v over pi times cubed root of 3v over 20 pi squared minus 2 thirds times the cubed root of 3v over 20 pi. This will simplify to h equal to the cubed root of 162v over 5 pi. So now we have an expression for the height and an expression for the radius.